All right. Okay. So we went through the case in which lambda is constant. We have seen that this implies a potential which is of an exponential form. And therefore is a sort of specific case. So one is free to assume a different kind of potential. And therefore, if lambda is not a constant, if therefore v prime is different than 0, then we can have a different potential. Okay? And you're free to choose the potential you want. Okay? I just mentioned a few stable ones that are quite that give reasonable solutions, reasonable universes, and they can be characterized in two main categories. One are the so-called freezing models. Where there is a moment in which, once the expansion of the universe starts, that the potential starts to freeze. Okay, the dynamics start to halve. One of these guys is the power law, so is a power exponential phi, which is a normalization term that can be to the power of m, so that's a constant 4 to the power of 4 plus n, where n is an integer larger than 0, and phi is minus n, so n is larger than 0. Okay. Later on, we are going to use this guy as an example. Then another one is this guy, so the phi, which is equal to m 4 plus n, so similar normalization term, phi to the power of minus n, so that's exactly the same, but there is an exponential at the end. Exponential of alpha phi squared over the Planck mass to the power of 2. Okay, so there is a scaling factor here, alpha, that let's say tune the relevance of the exponential term, and the rest is the same. So you see this potential would look like something like that. Okay, so that's our v of phi, that's our phi. This guy will look like this, so it's not bound. If the field starts to roll, it can go to infinity. Okay. This one is quite different, because there is an exponential term, which for low phi is similar to this one, but then it goes up exponentially. Okay? It means that the field is bound. It's not given this exponential term. If it's rolling down, cannot go to phi infinite. Okay? So the two are going to have quite a different behavior after the roll starts. On this side, the same would happen. Okay? But with a minus, with a reverse phi. Okay? But the behavior is going to be similar. If we look at this guy, qualitatively, it's going to be very similar, the behavior of the exponential one. That's because also the exponential have a shape of this sort. There is not a minima, and the phi can go to infinity. Yes?
As speaking, validity test for these models, shouldn't they can be mistaken for the cosmological constant?
So the cosmological constant requires no dynamics. So you need a phi dot equal to 0. Phi dot equal to 0, you can have it for this guy, but you cannot have it for this one. Okay? So you cannot, let's say observationally, you can confuse one with each other because you're not precise enough to distinguish one case with the other because they're very close with each other. That's it. Okay. Then there is another family family 2. I mean, there are several others, okay? I mean, there is like a full zoo of models. And it's called towing potential, towing models, which means the freezing. So they're kind of frozen at the beginning, so kind of nothing is happening, and then at a certain point, the fields start to evolve, and they are of this kind, with 0 plus n, 4 minus n, and phi n with n larger than 0. And you have like n equal to 2, 3, etc. And if you look, this is very close to the models of inflation. Okay. Inflation, the difference with respect to inflation is that they have 0 equal to 0. That's what we have seen, for example, in cosmology during the last term. Okay, there is this V0. What does it mean? That there is a plateau. Okay, therefore the potential look like this. So as phi is going to 0, this one goes to 1, and then something like that. Okay, so you see when we go at very large phi, this guy is going to be negligible. Okay, so this guy is going to be the ruling one, and therefore we have our plateau. So you see up here, unless you give initial conditions, they're crazy ones, it kind of frozen, you know, and then it unfreezes itself. Okay, and another one, just to complete a little bit the picture, phi is equal to m to the power of 4 cosinus to the power of 2, and then you have phi over some factor to tune the amplitude of, I mean, the phase of the cosinus. And this guy would look something like that. So it's periodic, therefore you have something, and so on and so forth. Therefore, you start up here, where it's quite flat, and again, this freezing thing, and you start to roll, and it rolls in this regime. Okay? And there is a bunch of those. So if this happens, if we are now going to assume a potential which is not the exponential one, some of those, then lambda is evolving as a function of time, as I mentioned earlier. And again, our phase space, x1 and x2. And we would have, for example, that the critical point, so we are going to have always the point A, B1 and B2 here, for minus 1, 1, and 0, fixed. But we are going to have A, which can be moving along this direction. Okay? Lambda would move, sorry, the point C would move in this direction if lambda is decreasing. Okay, so if we have some potential, among those ones, for example, that give us the condition for which lambda is going to decrease, then we know that we are naturally evolving toward the acceleration regime. And we are going to have a critical point that can give us acceleration. Okay? Whereas, so and here we have lambda 2 smaller than 2. Okay, so when we cross this limit for our C, then we have our accelerating point. Now the point, and in the same case, for lambda negative, we will move in this direction, again toward, from negative lambda, again still negative lambda, but again towards 0. So we are converging toward lambda 0 in this way. For the other guys, it's moving along a straight line. Okay. For our point D, BCD, yes, is going to move in this direction if lambda is decreasing. So we are going to have that. Okay? Good. So just to give you, to put all of this together. Nice. Now let's start to give a look at a few details. Okay? Let's go into assume a potential for having in mind something specific, which is this guy here. Okay, we get this guy here. Okay, if this is the case, the potential would look something like that. Okay, so keep in mind this plot that I will leave to you. That's the potential we are considering. So what happens if we are on that side, meaning v comma phi smaller than 0, right? As phi is growing, phi is getting smaller, therefore its derivative is smaller than 0. If this is the case, then lambda is larger than 0, just matter of definition, because there is minus derivative of phi divided v for lambda, right? V is positive, therefore this guy is going to define the sign of lambda with a minus in front. Negative v derivative of the potential, lambda is positive. Okay, so we know that we are on the positive side for lambda, and we know that we are on this side. Therefore, this is our phi. Here we have the 0, and we are on this side of the plot. And remember, you should remember that x1 is directly proportional to phi naught. Okay, therefore, it's positive growing in this direction. Therefore, x1 is going to be larger than 0. Whereas, if we are on the other side, if we are with this case, everything is reversed. But, if you look at the behavior of lambda, as the rolling is proceeding, so we look at the equation giving us the evolution of lambda, which is equal to square root of minus 6, lambda to the power 2, gamma minus 1, x1. Can be positive or negative. Okay? So if this guy is larger than 0, then the sign is given by x1. This is positive, this can be positive or negative, and if this is positive, we're going to see why I want this to be positive, then this condition, then this guy is going to be positive. x1 define the sign. Therefore, lambda, with respect to the evolution of n, okay, remember now we have a function, lambda of n is not a factor, a constant one, our lambda is going to 0. That's for A, that's for B. Okay? Ooh, that's nice. Because we want, whatever are the initial conditions, that our point C moves toward acceleration. And if in the far future lambda is going to be equal to 0, which is happening because that's what the sign of the derivative of lambda is constant, is given, and we know it's going to 0, we know that we're going toward the equation of state parameter for our field to be minus 1. No matter what are the initial conditions. Okay? It's going to evolve there. If, I repeat, if this condition is met. Okay? Therefore, if our gamma, meaning is larger than 1, then we are moving toward acceleration. No, that's the wrong word. Let's say that we give the possibility to have a critical point that allows acceleration. And lambda is going to become the effective, the equation of state for our field, so it is lambda, is going to be going to the direction of minus 1. So we have the possibility to recreate the conditions that we see in our universe. Okay? Moreover, this is called tracking behavior. It gives us the tracking, this is called tracking condition. Because if we start in a region of the universe where omega phi is much smaller than 1, and we know that this is the case in the past, not in all dark energy models. I need to show you that in the past we could also have the density of the of dark energy which is non-negligible. Okay, this can happen in the past with some model. But if we start from a matter domination epoch, we are going to have that phi, given the critical points that we've seen before, smaller than the one of matter, and we are going, and therefore we are going to have that rho phi is sort of catching up, okay? Catching up with respect to rho matter. Right, remember, rho, so the equation of state parameter tells you what is the speed at which the dilution of your fluid is going as the universe is expanding, right? W effective, of your fluid equal to -1, the density is constant. W equal to 0, the density is going down to the power of a to the power of -3, a to the power of -3, right? Matter, right? If, therefore, your equation of state is smaller than another one, it means that this guy, as the universe is expanding, is diluted less with respect to this one. Therefore, if you start with a density which is low for our field, density which is large for our matter domination, this guy is going to catch up. Okay? Is moving in the direction of the density of the matter field. Okay? Again, you see cases that are a little bit just because of that. Okay? You plug it in here. If this number is smaller, the dilution is lower. Okay? Therefore, if this is the case, you have rho, so the density of your field as a function of A. Then you would have matter, so let's do a log plot. So we have A to the power of -3 for matter. W for your field is smaller than this number, and I don't know, maybe it's doing like something like that. Okay? It is doing something like that because it tends at a certain point to be constant or close to constant because that's what we see out there. We are in the case, in the regime in which lambda is close to 0. Okay? So that's called the tracking condition, and this is the tracking behavior. Rho try to go in the direction of your field, try to catch up with the one of matter. And all of this is just coming up by looking at the behavior of lambda. Qualitatively, you see I picked up the exponential potential, so a specific case for phi, but the same scenario is going to happen also for the exponential potential. Okay, not just for this phi to the power of some number, but also for the exponential potential because it has the same shape, right? Therefore, the shape of the potential tells you what is going to be the behavior. Okay? The different slopes is going to change the time evolution at which everything is changing. But the qualitative behavior is the same. Good. Let's give a look at the origin. Let's try to give a better look at this condition. What's the meaning of this gamma larger than 1, smaller than 1, or equal to 1? Okay? That's what we had before. And by the way, if you look at your exponential, and you compute your gamma explicitly, given the exponential that we are assuming now, you see that that one guarantees this condition. So the exponential, the phi to the power of some number potential that we are considering so far guarantees this condition. That's a nice behavior for a potential. Okay, I can give the initial conditions I want, but this is going to happen. We are going to move in the universe that we see nowadays. Let's give a look at the origin of the tracking condition. I have myself by looking at the equation of state of our field. That again is going to be equal to 1 half square minus, then we have the potential over, what's that, 1 half phi dot square plus the potential, just the definition of our equation of state. Then we can group together V, and we get V is equal to phi dot square over 2V minus 1, and then we have V, phi dot square over 2V plus 1. V and V cancel out. And now I can define a parameter, and I call it X. Therefore, I can have this expression, which simplifies to that. So now I'm not thinking in terms of the phase space, but I'm just focusing my attention on the equation of state parameter of dark energy, and I reparameterize, introduce this new parameter, which I call just X, which is this guy here. Okay? And if you want, you can reverse the equation. So you can isolate this X term to look what is its dependency with respect to W. And you find this expression. Okay, I just isolated X and I found this expression. So the two are related in this way or that way. Okay, the inverse of the two functions. Okay, then for convenience, I call y prime the logarithmic derivative of this parameter X with respect to the number of e-foldings. I'm not going to do the steps because they are boring, lengthy, and they don't give any physical insights, but we can compute explicitly the X over the n. So we are asking ourselves how this X parameter, and therefore how the equation of state is changing. We are going to have some expression, lengthy, boring one. Then we again recall ourselves that everything can be expressed in terms of the x1 and x2 parameter. Okay, so wherever we are in the phase space, we know what is this guy. We can combine these two equations together, and we find that lambda, which is defined as V, phi over, well, actually let's do it this. We can then isolate all terms like that are coming from that expression, that we know to be minus lambda. And we get the solution. And the plus and the minus are given for phi dot larger or smaller than 0. Okay, we have this expression. So now, what's the trick here? We have an expression that tells us how X is changing as a function of the n given a certain lambda. Okay? And if we know how X is evolving, we know how phi is evolving. But now we are linking everything, not to x1 and x2, but to lambda directly. Okay? That's the detail. Then, other super lengthy and boring computations, we take these things and we get its derivative with respect to the potential phi. And we get an even longer and even more boring expression that is related to gamma. Okay, so you see, I'm making a derivative, therefore I'm going to have a double derivative here. And remember that in gamma, the double derivatives are contained. Okay, that's how this gamma is coming about. Okay, and this is equal to 1 plus 3 plus minus omega phi, W meta minus W phi, divided 1 plus W phi 6 plus y prime. It's not over. I would fill up the entire line if I would write all of it, so I will not. But we are going to have a function of y prime then we have W phi and all the other dependencies, but the key is that we have this dependency. And then we have another function, let's call it F1 and F2, which depends on, is directly proportional to, that's what it is. The key point is that this is directly proportional to y prime, and this is directly proportional, is a function directly proportional to y second. Okay, I don't write all the terms. You understand what I'm saying? So this is just an equation which is directly proportional to y prime, and an equation which is directly proportional to double derivative y prime, which tells us the evolution of this guy. Okay? Now, I don't write them down because under the assumption of that we're starting from a universe that is matter-dominated, therefore this guy is equal to 0, remember, a flat condition for the geometry of our universe, therefore if omega m is close to 1, this guy is close to 0. And if we are assuming gamma to evolve slowly, slow evolution, okay, then it means these two terms gives you an evolution of gamma, so this one is, we can set this one close to 0, we neglect, is evolving, but we neglect it because this guy is going slowly. This contains other terms regarding the evolution of our gamma, but again, this is going to be slowly, being derivatives, we can neglect. Not equal to 0, but is negligible with respect to the other terms. Okay? And we are left, damn it, the problem with these small boards. So let's do it here. So omega phi and the gamma slowly changing. Then this guy is becoming 1 plus Wm minus W phi, can keep, divided 1 plus W phi. So we have the 3, this guy goes away, this guy, also this guy is negligible, y prime is negligible, therefore we have a 3 divided with 6 that gives us that 2. Okay? That's the relevant expression that we were aiming at. So we have this one that we are going to use later, and this one. Okay? So we are focusing our attention on the evolution of the equation of state given a certain lambda, and assuming a certain gamma, which is slowly evolving. Having that, we can now isolate this term. Therefore, we're going to have an expression which is going to tell us what is the evolution of the equation of state given gamma. So let's do that. Let's take out this term, and we get W phi, which is approximately Wm minus 2 gamma minus 1 divided 1 plus 2 gamma minus 1. Okay, you see there is also a link between the equation state parameter for our dark energy fluid to the gamma parameter. And this guy is roughly constant. Why? Well, omega is 0 or 1/3. Okay, so this is fixed. And gamma can evolve, but we assume in first place that it's slowly evolving. Therefore, under these conditions, we see that W phi has a very slow evolution. And now what happens if gamma is equal to 1, that's equal to 0, that's equal to 0. Omega phi becomes equal to omega. Omega. W phi is equal to Wm. This is a scaling. Scaling. Same equation of state parameters, because these two guys are equal to 0. We are left with this condition. And therefore, we know that whatever is the evolution given a certain expansion factor, or the logarithm of the expansion factor, which is the number of e-foldings, and rho, they are roughly, I mean, maybe they have different values, but they are scaling with the same amplitude. Okay, one goes down, the other one goes down, and they follow each other. If instead gamma is larger than 1, which is the condition that we had before, which was the tracking condition, then we have that omega phi is smaller than Wm. And therefore, our field phi, the density of the field is catching up. That's tracking. That's the tracking condition. Okay? Our field is seeing the density of our matter somewhere and try to get the same value. Okay? And it's aiming, and it's aiming to omega phi is tending to become like omega m. Whereas in this case, omega phi over omega m is constant. And this condition is guaranteed for the first exponential that I showed you. Okay? So it's naturally guaranteed. So for, let me write it, m4 minus n, and then we have phi to the minus n for n larger than 0. Allora, look at gamma, just use the definition of gamma, which depends on v. So you have v, you have the definition of gamma that depends on v. You plug it into here, and you just get that this is equal to n plus 1 over n. And this is always larger than 1. Tracking is guaranteed for this potential. Start with the initial condition you want, that's what you're going to get. Okay, start with a negligible dark energy, but then at a certain point becomes relevant. Okay? Or maybe you can start, as we are going to see, with dark energy, which was relevant at the beginning, but it goes down with the power of -6. It can happen when we are in one of the corners of the phase space. Remember that those guys had a field-dominated epoch with equation of state parameter equal to 1. So we can start with a super large lambda, density contrast for omega. It goes down super fast. But then we can enter in the tracking regime, and then we start to catch up and try to go to get the same density of matter. Okay? Then the last thing, yes, I should be able to do it. I need those equations, so I will cancel T1. Is it clear so far? It's a bit boring, the steps, but the idea is we reparameterize the evolution of the equation of state parameter with respect to this of our field, of our dark energy, with respect to this guy, this x. Okay? Then is a little bit of mathematical machinery, actually very simple, just defining derivative of this guy, and we arrive at this relationship. So we are going to have the link between the evolution of x, and therefore W phi, with respect to lambda now, not with respect to x1 and x2. That's the trick, okay? Then we just get a derivative. We assume gamma to be evolving slowly, and out of this expression that we get by applying this derivative and assuming flat condition, we are going to add a super lengthy expression, but with this condition of slow evolution, most of it cancels, and we are left with this expression, okay? Out of which we can isolate W phi. And now we are also have the evolution of W phi with respect to gamma. Okay, so which describes the curvature of the potential. And since this guy is a constant, 0 or 1/3, this guy is slowly evolving, that's where we started from, then this guy is slowly evolving as well. And then this equation is also telling us that if gamma is equal to 1, these two guys are equal to 0, and we have that omega phi is equal to that W phi is equal to Wn. The two equation of state for the matter field and the dark energy field are the same. We have scaling. Their density is going to evolve in the same way. Okay? They're not catching up, they're not going to get one of the, they follow each other. Okay? Since the universe is expanding, we know that they're going down with the same rate. Okay? Good. Whereas, if gamma is larger than 1, and that's our tracking condition, then these two guys are going to be positive. Omega phi is going to be smaller than omega, it is omega. Our equation of state parameter for phi, no, the equation of state, non parameter, the equation of state of our field phi is smaller than 1 for matter, and therefore omega is going to catch up. Omega is going down in a certain way, but its steepness is lower with respect to the one of matter, and therefore the density of this guy is getting closer and closer with respect to this one. That's the tracking regime. And as the universe is changing, gamma can change, and when it meets this condition, you know, maybe our equation of state, our dark energy is completely negligible, but at a certain point, boom, I'm starting to catch up. Okay? And is going to become relevant, which is what's happening nowadays. So you see that's a key difference with respect to the cosmological constant, because with the cosmological constant you have one number and you have to choose it right such that nowadays we are roughly at this condition of similarity in the values between omega phi and omega n. Here that's not the case. With this potential, this condition is guaranteed, and you know that the two guys are getting closer one to each other. One this is met, okay? So you don't have anymore this fine-tuning, this coincident problem that you need to solve, okay? Come out quite naturally from all the derivation. Okay. Then the last piece of terminology that I want to give you. And of mathematical machinery which is out there, which are the so-called tracker solutions. It's very related to that. It's very close to that. Which time do I have? Okay, yeah. Tracker solutions. Okay. Now we can use the equations that we have up there and reshuffle them a little bit. And out of this expression, we can isolate this term. Okay, so let's make it red. And we get this expression. So I'm just isolating this term out of this equation, nothing more than that. So we have 1/6 the ln x over the n equal to lambda square root of omega phi divided 3, 1 plus w phi minus 1. And I call all of this guy big delta, which is evolving as a function of time, as a function of n or whatever. Okay, it's something that is changing as a function of time. We see it here, minus 1. So I'm defining this guy, all of this as our delta. And you see it's a combination of lambda, omega phi, and w phi. But it's the guy that defines, that tells you if x is growing or decreasing. That's the importance of that. Okay? You see that if delta is larger than 1, then x is increasing. If delta is equal to 1, then this is 0, x is constant. And of course, if delta is smaller, sorry, where am I left? Delta smaller than 1, yes, then is negative. X, this guy is negative, so x is decreasing as a function of time. So this combination of factors that we collapse into this gamma tells you what is the behavior of W phi. Okay? The x, what is logarithmic, so the ln x over the n is equal to 0, larger than 0, smaller than 0. So it tells you that. Okay? That's what delta is telling you. So it is smaller than 1, equal to 1, or larger than 1. Oh, the way around, sorry. Tuck and tuck. No, what the hell, it was right. Okay, you know what I'm saying. Okay, positive and 0, God, now I'm, so positive, then larger, negative, more, okay. Good. Then, we know this evolution. We can go back to x, okay? We just use the definition of x, which is just 1 plus w phi over 1 minus w phi. That's what we have up there, okay? That's just coming straight out of the definition. And our the ln x over the n, so I just compute explicitly this derivative. Okay, so you see I'm computing the derivative, not using this expression that was with respect to our beloved lambda, but with respect to definition of x, which contains our w phi. Okay, same guy, but computed into different ways. Therefore, that's a logarithmic derivative, so that's 1 over x, the x over the n, and just make your derivative x. Plug in, get your derivative, and you get this expression, 1 minus w phi over 1 plus w phi, w prime phi 1 minus w phi, plus 1 plus w phi, w prime phi, with respect to, where is it? 1 minus w phi to the power of 2. Then you have things that cancel out, as well here you make the product. There are things, you see minuses here, plus here, they cancel out. And you're left with w prime phi times 1 minus, they cancel, so we are left with, whatever. We are left with phi 1 plus 1 will give us a 2 over 1 minus phi squared. The mistakes should be, yes. Okay. Yes. We have this expression. Okay, so we have two equations that relates the logarithmic derivative of these two guys, of x, okay? And the two must be the same, right? It's the derivative of the same thing. Therefore, I can make, I call it equation A, equation B, and I can then impose equality because they must be the same, so equation A equal to equation B, and we get the omega phi over the n equal to 3 delta t minus 1 times 1 minus w phi squared. Okay? Relation to lambda, from the straight definition of x, the two have to be equal. I have this equation. And you see, now that we have an even better representation of W with respect to delta. Because this equation is telling us the derivative of the equation of state of our field with respect to the number of e-folding is larger or smaller than 0 for delta larger and smaller than 1. That's the point. So we basically collapsed all the information regarding the derivative of W phi into this delta. And this delta is going to tell us, so you see from x, which is, this parameter, but this parameter is not the equation of state, W. So I went through its definition to get back a link between delta and the evolution of the equation of state. That's what we did. Okay, it's a little bit of mathematics to arrive here, but that's the key point. This guy is going to give you the tracker or not. If gamma is going equal to 1, you want, for example, to start with a W phi, which is perhaps very large, 1, which is the maximum that you can have, and then maybe it's going down, but then at a certain point you want it to go back, for example, such that you enter in the tracking regime. Once you get your delta equal to 1, you enter in the tracking regime, and then you start to catch up. Omega is gone. You want to enter in the regime in which omega field tries to go back to your omega m. Okay? And this gamma, this big delta, contains all of that. So it's a way of collapsing the information in one single number. Then, this equation can also tell us something different. Sorry if I write it here, but I don't want to cancel the board again. So if we get x, which is evolving slowly, that we know from before, because we had our gamma, which was evolving slowly, therefore we know that this equation, so this derivative, is close to 0, because of the slow evolution of x. Therefore, we can get our expression of A roughly 0 because of this reason. If we do that, what do we achieve? That's equal to 0. We can get omega. We can isolate, even though you have this guy equal to -1, we can isolate omega. We isolate omega, and we get even the expression for omega phi, which is roughly 3, 1 plus W phi over lambda square. Okay? What's happening if lambda is going towards 0, as we've seen it's doing? Omega phi goes up. Okay? It's growing, which is exactly what we were aiming at. Okay. Good. So, we can stop here. Well, one thing that I wanted you to notice is this one. Look at this guy. Now, the table I wrote you before is gone, but what is this guy? What is this corresponding to? To the point, to the critical point, should be the last one, which is D. So the universe is forced, given this condition, to go to the critical point D, which is this guy here. Where, if you recall the table, omega m is equal to omega phi. So now we are not at the definition of the critical point. But we are going in the direction, the tracker solution tells you that your solution must go here. And your universe must evolve in this way. Okay? Then lambda, remember, is not fixed, it's changing as a function of time. And from a stable point, because you start from a stable point, you become unstable. Therefore, you are trapped there for a while, but then you're free to move to the point C, which is the one with the acceleration. Okay? So today was quite a dense lecture. but the concepts are not many in the end. So I wrap it up. So we are looking what is the evolution of our universe in terms of omega m, W phi, so equation of state parameters, and density contrast of the species that we are considering, namely one matter component, and with matter I mean radiation or dark energy, dark matter or baryons, and our dark energy field. Okay, we used our phase space approach, in which we can, with two numbers, x1 and x2, know all of this in one shot. Okay, then we study the Klein and Gordon equation combined with the Friedman equation, apply a perturbative approach to have a set of equations that tell us what are the critical points in our phase space, right? So we had our two equations telling us what is the evolution of x1 and x2, and we are looking for very specific solutions, those for which there is no evolution at those locations, okay? We've seen that no matter what's lambda we are going to assume, we have three fixed points that are at the edges of our field, of our phase space, one in the middle, two that are unstable or saddled, therefore we are always running away, and we are running away because we are on the edge, we cannot, escape in any other direction. We have a saddle one, one can be saddled in the middle, and therefore we know that our solution can do something like that. I gave you the case for lambda equal to 1, this would be the case. Then we have other two possible critical points, which was one that provides acceleration, and this is sitting on the circle, along the circle, given a certain lambda. We can have or not acceleration, according to the fact if lambda to the power of 2 is larger or smaller than 2, right? There is the condition W effective that you impose, and you know what is the lambda for which you have the expansion, moving along this circle, okay? Then we have another critical point that gives us another matter domination, in which the equation of state parameter is similar to the one of the field, okay? We can have the two, but they are behaving exactly in the same way with respect to the pressure contribution. And these points can move around if lambda is evolving as a function of time. We have seen that, okay? And if lambda is evolving as a function of time, it means that we are not assuming an exponential potential for dark energy. So for an exponential potential of dark energy, lambda is constant and the fixed points are, boom, there. You fix lambda and these are the critical points. You don't move from there, okay? Whereas with other exponentials, such the power law that we are using in this case, lambda prime is different than 0. Therefore, it can evolve. And we have seen that lambda naturally evolved towards 0, which is a very good behavior. Because if we go with lambda equal to 0, we are going to have our critical point C, which is moving in the regime in which we are going to have acceleration, and we are going to move in the regime where the equation of state of the field, of our dark energy field there, is the one that we are looking for, -1, or something close to -1, okay? And that provides acceleration. That's what we were looking for, okay? So this, we have it, and then we have seen some other things. We defined we realized the fact that given certain conditions, we have related to the behavior of gamma with respect to 1, if it's larger, equal, or smaller than 1, we can have a scaling solution for which omega phi is going to be equal to, so W phi, where is it? Is it gone? Yes, it's gone. Okay, but anyway, you remember that we have the scaling conditions in which the field and matter, the density contrast of field and matter goes along one each other, okay? There is no one that is getting larger with respect to each other, they follow each other. Or, even more interesting, we have these tracker solutions that occurs when gamma is, when we assume that gamma is slowly evolving, and if this delta factor that we derived with this mathematics, with this mathematical machinery, if this delta is going to be larger or smaller than 1, then W can be growing or decreasing. The equation of state of our field is growing or decreasing. And with our gamma larger than 1, we know, with our delta smaller than 1, we know that this guy is going to decrease. He's going to move in the direction of -1. Okay? Naturally, it's going to go there if this condition is met. Okay? So, this is it. During the next lecture, we will go once more through the critical point, because it's like, you know, is important, because even if we're going to study modified gravity in this sort of models, then we go always back to the study of critical points. So it's good if we go a little bit back to that in the full picture, with radiation, matter, and dark energy. And we are going to see how delta is changing as a function of time, and how the equation of state parameter is changing as a function of time as well as all the other species. And we will have the full picture with a solution that involves tracking. Okay, so it is tracker solutions. So you will see all of it. Once we are done with that, we will start to look into dark energy, which is interacting with matter. So now it was a self-interactive field, no interaction with matter. We are going to use interaction, a field which is interacting with matter. Once we are done with that, we will start to look into modified gravity. Okay? And then we will see how also we can transform a modified gravity theory into a dark energy theory and the way around. Okay? And we are going to see how they are quite equivalent one to each other. Okay, good. So, thank you very much. Sorry if I took 10 minutes more, but I wanted to finish this. Thank you very much. See you next time.